Now next, let's do section 1.5, where we do exponential and logarithmic functions, which are slightly more interesting than what we've been reviewing. Now, exponential function is different from the polynomial in just only slightly, but a lot. That is, here's a polynomial, a basic one, equal to x squared. The exponential function is something like, let's see, we have a g of x equal to 2 to the power x. Now they look similar, but the story is very different because your variable is actually in the exponent itself, and the exponent it grows fast. That's the difference. For example, like it doesn't grow fast at first, especially if it's less than 1, especially it doesn't grow at all. But once x get past 1, then it start to grow fast. Like for example, in your book it demonstrates the two graphs of these things. You see, if when y equal to x squared is growing quickly, but y equal to the power x grows even better, and the bigger it is, the difference becomes huge. That's where the saying exponential growth comes from. So the exponent, just remember that the variable is on top, which makes it not a polynomial. Okay, a polynomial only have x on the bottom with a number fixed constants as on top as the power. Okay, so moving along, let's see. Okay, next, let's look at rules of exponents. The rules of exponents are identical to other algebraic rules, which is something you should memorize, like like the back of your hand. You should know that than anything, really. So the rules of exponential functions are when you have two things multiplied together, b of x times b to the power y, that the exponents add up, which is very convenient. And similarly, in division, b of x divided by b of y. By the way, the numbers b is a number. Okay, it's a constant, whereas x and y are variables. That's just tradition in math to do things that way. So b of x, when you do division, it translates into subtraction. Next, and when you have power, let's see, what's this? Okay, b of x to the power y, that translates into multiplication, xy. And notice this b of x itself is being raised to the power y, so that's a lot. And that translates into multiplication, and then the next rule is when you have two things multiplied together, like that. What is that? X equals to bx. So when you have a power setting, then the power will be distributed to each one. And then in terms of division, similarly in division, it works the same because multiplication and division are kind of the same thing. So ax over bx. Now these things you need to remember them like it is the purpose of your existence for as long as you're a calculus student, or algebra student, or in anything like high school math. You have to know this, okay, to survive in calculus. Really, this need to be known. If you have a hard time remembering it, then it should be written down at the front of the book or something. And every time before you do calculus homework, look at the stuff to remind yourself. That's if you have trouble remembering it. And all right, I think this side is dried up. All right, so we will do some examples because being able to use these formulas are very important in algebra, trigonometry, calculus, all those things, because you do that like all the time. So anyway, so let's do some quick example, I guess. Let's do example 1.34. This is example 1.34, where you have some kind of a thing, so some made up problem. All right, so we have a expression. This thing is called an expression. 2x 2/3 and 4x minus 1/3 and 2 to the power 2. Okay, now expression is different from the equations only because equation has the equal sign on it. If you just have a thing by itself, it doesn't equal to anything. It's just called an expression. Now, so we have that thing, and we have to get it to come out by using these things. So they are simpler. So you have so that equals to 2 to the power third, x to the power 2, okay, 2/3 times 3, because of this rule. It multiply power outside power, and then divided by 4 to the 4 squared. 4 squared is 2 to the power 4. I change it to 2 so that we can do easy stuff later. And x to the power multiplied, that's just minus 2/3. All right, so that gives you that's 3, that's 4, so you got 1 left, one of the 2 left. Okay, and that's 2 minus 2/3. You have x 1 and 1/3, or 4/3 left on top, like that. No, sorry, it's subtraction. Subtraction, you actually add. So when you add, is 2 and 2/3 left. What's 2 and 2/3? 2 and 2/3 is 6 plus 2 is 8. 8 over 3. All right, so that's that. And this thing is your answer to simplify this thing. All right, so that's that. And having said that, let's move on. Next, we look at the number e. What's e? The number e has to do with compound interest. For example, when you put money in the bank, it generates, and let's say you calculate the interest once a year. It follows some kind of a formula that looks something like this. A of t, A is the amount, total amount, t is time. A of t equals to your principal, what is that? 1 plus interest to the power of time. Okay, now so that's your compound interest, and let's say that's compounded once a year or something. But what if you compound it every 6 months, so only half a year? Then the formula accounts for itself. And without going too much into details, being that we're just reviewing, I just want to quickly mention this. So once what if you compound more often, then your formula changes somewhat to account for it. Say compound every half year. But what if you compound every month? Okay, fine, we'll compound every month. What if you compound every day? Every second, every millisecond? And you're probably wondering, why would we do that exactly? Don't ask. The point is, if you compound it instantaneously, like every nanosecond or something, you eventually arrive at some kind of a thing that looks like this. 1 plus 1 over m, this particular m. And this particular thing here, as m increases, it settles down into a specific number. That's 2.718. And this number has a name to it, and it's called e. And e and pi are the two numbers in the math world that has its own name. Okay, pi is 3.14, and e is 2.718. So and e is an important number for various reasons, but we're not going to go into that right now. Just recall what e is. And what matters is that e in logarithm, base e has its own name, but we'll cover that in a little bit. Okay, flipping pages, that's enough compound interest for now. Let's move along and consider logarithm. What is logarithm? Logarithm is this way of talking about things. Okay, now say for example, a logarithm is when if you have b to the y equal to x, which is fine, b to the y equal to x. What about it? There's another way of saying this, is that if this is true, then we say log of log base b of x equals y. This is what this means, okay? It's just another way of saying this. And why are we doing this? There are convenient reasons why we're doing this. So, and then you have to worry about the domain and the range, because things that go into power has to be positive, otherwise it gets weird and confusing. So all this stuff, yeah, it has restrictions on domain and range and stuff. And generally speaking, logarithm function, the domain is restricted to the positive numbers, but the range can be whatever. Okay, so yeah, that's just a thing that you bear in mind, and that's good enough. An example of logarithm is that, for example, what is log base 2 of 8? Oops, what am I doing? Let's calculate log base 2 of 8. What is that? That is asking the question 2 to what power equals 8? 2 to what power equals 8? That would be 3. So that's your answer. And then and always, what is the log of 1? That is well, what base is that? Well, it doesn't matter. Some base, 2, 5, something, 1,000. 2 to what power equals to 1? Well, there's only one thing that would be 0, okay? Because everything whose power is 0 is 1. So the answer, log of 1, any base, is 0. Okay, let's move along. The logarithm graph is, being that the log is the inverse of the exponential function, the logarithm graph is a mirror image of the exponential function, because they're the reverse. Anyway, yeah, that's good enough. Move along. Flip. What's that? Okay, log properties. The logarithm properties comes from the exponential properties. They're the same. They're the same thing described in a different way. That is, multiplication translates into addition, just like this one. Okay, for example, log of a times c, let's say, is the same as log of a plus log of c. Like that, right? Yes. And similarly, division, log of, you say what base? No matter what base, just as long as the same base. Log of division, log of a divided by c is the same as log a minus log c. And the same as power. When you have power, the similar situation is log of say a to the power r. Excuse me, my helmet is falling off. There. Actually, that's not a helmet. That's just a headphone. Whatever. So the exponents log of something a to the power r. That's the same as r times r log a. Okay. Again, any base. So we don't write down the base as long as it's the same base. Okay. It doesn't. Of course, you throw in a different base, then you're not making any sense. But anyway, so those are the rules. All right. So next, let's do some exponential equations. Equations involving exponential functions